Welcome to our lesson on how astronomers measure star temperatures from colors. Have you ever noticed that stars in the night sky have different colors? Some appear bluish, others yellowish like our sun, and some even have a reddish tint. These colors aren't just beautiful to look at, they actually tell us something very important about the stars, their temperature. To understand how we determine star temperatures, we need to talk about blackbody radiation. Every object with a temperature above absolute zero emits electromagnetic radiation. The hotter an object is, the more energy it radiates. But it's not just about the amount of energy. The peak wavelength of that radiation also changes with temperature. This relationship between temperature and peak wavelength is described by Wien's displacement law. It states that the wavelength at which an object emits the most radiation is inversely proportional to its temperature. In other words, as temperature increases, the peak wavelength decreases. This means hot stars emit most of their energy at shorter wavelengths, appearing blue, while cooler stars emit at longer wavelengths, appearing red. Our sun, with a surface temperature of about 5,800 Kelvin, peaks in the yellow-green part of the spectrum. Astronomers use this relationship to classify stars into spectral types. The main sequence ranges from hot O and B class stars, which are blue, through A, F, G, and K, to cool M class stars, which are red. Our sun is a G class star. Many astronomy students remember the spectral sequence using the mnemonic, "Oh, be a fine girl/guy, kiss me." But how exactly do astronomers measure star temperatures? They compare a star's brightness in different wavelengths or colors of light. A common method is to use color filters that only allow specific wavelengths to pass through. For example, astronomers might use a blue filter, B, and a visual filter, V, to measure the star's brightness in those two colors. The difference between these measurements is called the BV color index. Hotter stars will be brighter in blue light compared to visual light, giving them a more negative BV index. Cooler stars are brighter in visual light than blue light, resulting in a more positive BV index. This method allows astronomers to measure temperatures quite precisely, even for stars that are extremely far away. One complication in measuring star temperatures is interstellar dust. Dust particles in space scatter blue light more than red light, making stars appear redder, and thus cooler than they actually are. Astronomers call this effect reddening. The density of interstellar dust is typically about 0.1 atoms per cubic centimeter, but over the vast distances between us and other stars, this can significantly affect our observations. Astronomers must correct for this reddening to get accurate temperature measurements. They do this by comparing multiple color indices and looking at the star's spectrum in detail. To summarize, astronomers measure star temperatures by analyzing their colors. Hot stars appear blue because they emit more energy at shorter wavelengths, while cool stars appear red as they emit more at longer wavelengths. By comparing a star's brightness in different colors, astronomers can determine its temperature with remarkable precision. Next time you look at the night sky, remember that the beautiful colors of the stars are actually telling you about their temperatures. The blue stars are the hottest, yellow stars like our sun are medium, and the red stars are the coolest.